So now that we have that Lewis relation from part 1 of part A that we just discovered, we can actually go ahead and use energy balances, and with that we can find the relative humidity of that wet bulb, dry bulb temperature. So, to start us off with this, we're going to need to use the rate of enthalpy lost from the thermometer. And the equation that we're going to use with that is this heat of vaporization times that mass transfer coefficient times the molecular weight and we're using the concentration from the surface to the concentration away from the surface here. And we're having that equal to the heat transfer from away from the surface to close to the surface. So by that I'm talking about having that heat transfer coefficient. We're having that temperature away from the surface subtracted by close to the surface. And from here, this is where we're going to use our Lewis relation that we just found out. We're going to take both sides of these and we're going to divide it by that mass transfer coefficient. And the reason why I'm writing it like this is this allows us to get rid of it. Cancels out on that side. Here, we just found that in our last problem. We said that those two values are equal to rho Cp. I'm going to go ahead and do that. And so we're going to go ahead and change that there. Now, Cp is the heat capacity here too, and that's the density, but with that we can go ahead and change that here, and we're going to rewrite this as that heat of vaporization times the molecular weight times the concentration on the surface, concentration far away, equals to that rho Cp, the temperature far away and close to. And the reason why we're writing it like that is we're actually going to want to work with partial pressures here. And why we need this here is because with partial pressures we can get the total pressure here and the temperature average. Because we're going to rewrite this right side, we know that this value is equal to that heat total over that times the temperature average. So with that in mind, sorry, I wrote it right here. The P total, the pressure total, time over the universal gas constant times the average temperature. And so with that in mind, we're going to rewrite that here. But we're also going to have this multiplied by that molecular weight average. We're still having that S. There we go. And so on the left side, we're going to have to rewrite this here too. We're going to use these concentrations here, and we're just going to write those as the partial pressures. We're keeping these two values here though. So the way we're going to write it the same way here, except this is the pressure of water from the surface over that universal gas constant times the temperature of the water from the surface minus the pressure of the water away from the surface over that universal gas constant times the temperature of the water away from the surface. So that gives us the partial pressures that we can work with, but now we are going to have to get rid of some values here. The easiest one we can do right now is this universal gas constant. If we pulled it out here, it's 1 over the universal gas constant, that's 1 over the universal gas constant, goes away. But another thing we can work with is these temperatures right here. Now these temperatures right here are actually close to being equal to each other. They're not exact, but they're such large numbers that we don't have to worry about it. If it's just a little bit off, it's not that big of a deal. So we're going to go ahead and assume that those are the same values. Roughly the same values. And so with that in mind, we're going to go ahead and cancel those out too, because since they are all equal to each other, we can again pull this out and it'll cancel out on both sides. I'm going to go ahead and rewrite this just so that we can see how it's now written. It's a little bit messy right now. But now we have that pressure of the water at the surface minus the pressure of water away from the surface pressure total, heat capacity, and so on and so forth. And actually, we can work with what we have here because this helps us to find the relative humidity. Now, the relative humidity we can derive from this. We know that that is the pressure of the water at the surface all over the pressure, saturated pressure of the water at certain temperature T. Now, from this equation, we can find that pressure of the water of the surface. It's right there. We can figure it out from there. And on this one, we can find that saturated pressure using Antoine's equation. Very poorly written, but I hope you can read that. And so from that point on, we're going to have to move to part 3,